Yeah, so up next we have Markus Ritsch, who is Vice President of Water and Earth Technology, who's going to speak on maybe saving some maintenance on rain gauges. So Markus.
Yes, can you hear me?
Yeah, I can hear you now.
Yes, I can hear you.
And if you can, there you go. And your video is off, just so you know.
My video's off?
Yes. There you go.
Can you see that?
Yeah, your video's on. Go ahead and share your screen again.
All right.
Looks good. Go ahead.
All right. Well, thanks, everyone. I'm going to continue on the afternoon topic of field-focused efforts and projects that we have going on. As Ron mentioned, my name is Markus Ritsch, and I'm with Water and Earth Technologies. And I'm going to talk about a little project that we completed to provide some automation for all-season rain gauges that typically require some manual effort. So all-season gauges are not typical parts of a flood warning system. We usually deal with tipping bucket rain gauges because they're easier to deal with. They don't require as much maintenance, and they provide the information that we need for flood warning. However, they're not always the most accurate type of rain gauge, and in some situations we do have gauges deployed that will monitor rainfall to a higher degree of accuracy, especially in higher rainfall rates, and we refer to these as weighing rain gauges. So they're meant for all season operation. They measure rainfall in the summer and then snowfall in the winter. They typically can measure to 1/100 of an inch. And the system that we started with for this project is a model NOAA 2 manufactured by ETI Instrument Systems. And so this gauge is based on an antifreeze charge in the winter. And you need the antifreeze because the antifreeze melts the snow. But the problem with these gauges is that when they fill up, you manually need to go to the site and drain the gauge and then recharge it with new antifreeze to continue to measure snowfall. So if you purchase a NOAA 2, this is what it is delivered. There is a large collection chamber, which is 12 inches in diameter. At the bottom of the collection chamber, we have a door. If you open the door, you will see inside of that a weighing measurement assembly and a manual drain. So that black hockey puck looking thing contains a load cell, and that actually measures the weight of the fluid inside the collection chamber. When that collection chamber fills up, you go to the gauge and you open that manual drain valve, drain it down, and then you can continue to operate. The photo on the right is looking down into the collection chamber to the bottom of it. And so this is a typical weighing rain gauge, whether it's manufactured by ETI or GeoNor or OTT. So let me back up. So the measurement principle of this gauge is a load cell, and it provides a tipping bucket type pulse output for every 1/100 of an inch of accumulated liquid inside the collection chamber. When the chamber fills up, a manual trip to the site is required to empty the collection chamber and to continue the operation of the gauge. So you can see that during the course of the season, you could make several trips to the site to keep it in operation, whereas a tipping bucket rain gauge doesn't require near as much effort. So our goal was to come up with a way to reduce the number of trips that you make to these sites to empty them. And in an ideal world, you might want to visit it once in the October season before it gets too cold. You would charge it with antifreeze. The gauge would run all winter collecting snowfall. And then in the springtime, it would automatically drain itself and then continue to collect rainfall during the summer season. And then you would go back and visit it once again in October. So what we did is introduce some smarts into the gauge. We added a programmable data logger. We added a solenoid valve, which we could control from the data logger to drain it. And then we determined what time of year we could drain that gauge to avoid any possible freezing temperatures. So for us, that was May 1st. And then we also wanted some mechanism to let the end user know if we didn't get a successful drain that a trip would be required because we have a plug in the drain valve or something like that. So we wanted some method to notify the user if things weren't working. So the first thing we did was we added a debris filter to the gauge. And the reasoning here is that these gauges are typically open to the atmosphere, and during the years or during the year, leaves, dirt, and debris will accumulate inside the collection chamber. And we didn't want that debris, when we automatically open the valve, to clog it. So we added a debris filter. And so this is the debris filter. It's just a pad, a coarse hair pad that is cut to the exact dimensions of the collection chamber. And then that gets pushed down to the bottom. And that is what prevents the debris and leaves from entering the drain valve. Next, we added a filter before the solenoid valve. Again, this was a precautionary measure so that we don't have any fine debris going into the solenoid valve. So this has a little removable filter on it. You remove that cap and there's a screen in there, so you can pull out the screen, clean that off, and put that back in place. And the idea is that every October you would just clean this screen as part of your annual maintenance there. Then we introduced the solenoid valve, which we could control from the data logger. And now underneath the gauge, this is what it looks like. So we've replaced that manual drain valve with a filter and then the solenoid valve. And then behind that solenoid valve is a relay. And then the data logger is programmed to activate that solenoid valve after May 1st to drain it, and it will continue to collect precipitation during the summer. The data logger is actually programmed during the summer to continue to drain it. So if it were to fill up a second or a third time during the summer season, it would continue to automatically drain the gauge to allow it to operate for the entire season. And then we plumbed the drain valve out the back of the gauge. And then this is then connected to a receptacle, or you know, the waste fluid is collected from that hose that extends from the back of the gauge. So the last piece of the logic on the data logger is what happens if the data logger notices we don't actually get a successful drain. So the data logger knows exactly how much liquid is in the collection chamber. And if it opens the solenoid valve and water is not being reduced in the collection chamber, it says, all right, I have a problem. I have a clog in the solenoid valve. And in that case, it will actually pulse the signal line 300 times spaced at a 1 second interval. And this data is then transmitted, and then the user would see this large pulse count and recognize that that's an indication that I have a problem with the gauge. And unfortunately, at that point, a maintenance trip is still required. So the retrofit that we completed on that gauge would essentially provide for partial unattended operation, so that we still have a trip in the fall to charge the gauge with antifreeze, but we have fewer trips during the year to manually empty the gauge if it gets full. So the next steps would be to actually introduce a pump and a reservoir of fresh antifreeze so that the data logger can drain it automatically and then recharge it with fresh antifreeze. And this configuration would essentially provide complete unattended operation. And so on the right there, we have a photo of a system that we put together to do just that. So you've got two 50-gallon drums at the base of a Roan tower. We have a pump at the base of the Roan tower. And one drum is empty and the other has fresh antifreeze. And then the gauge pretty much tracks the collection chamber. And if it gets full, we'll drain it, recharge it with antifreeze. And this gauge theoretically could run unattended until we run out of fresh antifreeze. And that's the end of the presentation.
Okay, let's give it a minute for some questions here, see if any pop up.
Okay. I think I put us ahead of schedule.
We're ahead of schedule now. That's good. We got a lot of stuff to and people to talk and give updates, so it's all good. There, you got a question?
Have we been able to test it? So we have tested it. So NCAR in Colorado, which is the National Center for Atmospheric Research, actually uses the automatic drain and fill gauge at their high elevation research sites. And the auto draining gauge that I showed you there is actually going to be put into operation by Ron Murato this fall. So we will get some feedback from Ron on how the auto draining gauge works. All right, we got another question. Can you discuss the options for antifreeze related to environmental impact concerns? So the antifreeze in protected areas does not get drained to the ground. So we typically deploy a receptacle to catch the waste antifreeze, and it does have to be removed manually. So in Colorado, for example, the NCAR group actually rides in on horseback to these high elevation sites once a year, and they remove those 50-gallon drums with horses. We are looking at other ways to evaporate waste antifreeze so that you don't have to manually remove it. And so those are some of the areas that we're doing some research on.
Okay, great. Thank you, Marcus. Appreciate it.
Thanks, Ron.